What's up, Mine's Formula here. Back at it again with another banger video. Today we're going to be talking about buckling. Even though it's just some pin joint, throwing some of that BS. But you know what we're doing today? We're looking at some cool buckling. You know what buckling is? Knock. That's why you're here. Alright, big ass cornball inbound. Skip. Yup. Straight to the point. Alright, we got some buckling, okay? What the flip is buckling? You're just looking at this graph like, oh my god, he skipped it straight to it. Ready? Buckle. I apply load. Boom. 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 Yes. That's a long column bending. Thank you. So, back to the point. It looks like this. I just teased you guys. So, that's what it like more likely looks like. So, you know, this happens because, you know, for some reason, you know, out of plane forces be moving around and it just fails. You ever have like one of those super long pieces of sheet metal and something, and they go whoa, 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 whoa. Kind of a very similar principle here on how they make the noise and everything. It's really, really cool. But anyhow, so what is it more mathematically? So if we like want to, let's say, look at this diagram, we define it as this Euler safe region. And this is a really good safe approximation, especially as we get over on the left side of the graph. And everything on the right side fails, right? So, and what is this safe region? So this safe region is based on your geometry and your material properties. And it's pretty cool how it works. And based on that, it tells you what critical load you're going to have before it buckles. So you can kind of see here they're talking about axial load, and this is specifically only compressive axial force. So you can't buckle when you pull it or anything, right? You just want to make sure, sanity check, right? So now more jargon, blah 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 blah, or simply factor of safety is less than the yield strength, right? So it happens before it actually gets to its official yield position. So you could have, let's say, 30 KSI in a part and it doesn't fail, right? But let's say it's super slender and thin. There's actually a high chance it'll fail in buckling first than that axial force. So you kind of need to check your buckling, especially when you have slender geometry. So anyhow, and for this, we're going to talk about, you're going to see this P critical. There's also a sigma critical, which is really just P critical over A, same thing. But it's, like I already said, it's the strength of the column rather than the strength of the material, so it's a little different. And that's where you want to use it separate from everything else. Kind of similar to bearing stress and tear-out stress, right? It's separate. It's a kind of a specific case study that you just need to check so it does not, fail in that case. So here we are on this lovely diagram, and you're probably thinking, what is all this junk? So first we have the big equation right here, up here. This is a really good equation. And what each of these terms mean, so you can see that is equivalent to your stress critical, right? F over A. You can also rearrange it so you just have your P critical. But this SR value is what we call the slenderness ratio. And what the slenderness ratio is it's this L effective over your K, which your K is your radius of gyration. And we'll talk about what this L effective length is. But based on your fixture setup, your effective length changes. So and then I'll talk about that in a second. But just keep that in mind. And then your radius of gyration is based off of the dimensions of your beams, of your moment of inertia, and you have your area at that location, right? So now we get to here, same thing. They use C. There's a bunch of different things you can do, but this is a lookup thing that you need to do. So the better of a lookup you can get, the more accurate of a result you're going to be able to make. So let's say you have a weird testing scenario and you find some case study online and somebody gives you these values. That's great. That's really, really useful. And you should probably use those. And for what we do in these basic scenarios, it's widely known for the L effective to use these values. So there's depending on how you want to look at it, you could use theoretical AISCI or AISC, sorry, and there's a conservative one. We use this middle column right here. This is the one that I would recommend using. And for, let's say I have a fixed free, so this middle one, right, fixed free loading case. Well, I'm going to come here and be like, all right, well, I have a couple different options. Well, I'm going to use this middle one because that's what we want to use, and it's 2.1 times my length. So that's now my L effective. So it's pretty simple once you figure out what you're doing. There are some weird cases where you're like, well, what if I have a these don't represent every single option. Especially with these rounded ones, these can be a little weird. So you got to be careful. And as well as this new region. This is like the storm in Fortnite, okay? Like two different regions entirely, okay? So we got the Johnson region now. Now why the hell do we have the Johnson region? Because that, you see that little corner right here? That's kind of just like unnecessary overcalculation. Like that's extremely safe. And it doesn't model it very well. And basically the big thing to understand between the Johnson and the Euler line, right? And the Johnson's on the left, Euler on the right, is that they intersect at this point where it's called the SRD, right down here. That is based off only your material properties. And it is different from your SR. They are not the same. Do not mix them up. SR and SRD are entirely different. And you will see that based on the relationship between the two, it'll tell you whether to use your Johnson or Euler region. But anyhow, with the Johnson line, you have this new set of equations that you have to use. So very, very similar to the Euler line. Now you have this new equation you're going to plug and chug for a better line of fit. So same thing, you got your SR, SYC, which is your yield strength, and Young's modulus. There's different ways to combine it, whatnot. All the same thing. Just different convenient equations in case you want them. And then, so this is the big part that you guys need to understand. So the SRD and the SR. So the SR, like we mentioned earlier, is the effective length divided by your radius of gyration. That is like just the x-axis on this graph down here, right? So, and the SRD is the intersection point between the Johnson and the Euler line. And this point is defined by this equation here. This one is really important to know because it tells you whether to use the Johnson or the Euler. And it's pretty straightforward. You're like, okay, you can memorize it like with this little formula. You can always just think it in terms of the graph. If my SR value is greater than the SRD, I'm going to be on the right. If it's less than the SRD, it's going to be in the Johnson, right? Same thing as what it's saying right here. So, yeah, there's not too much more to this. It's pretty simple, straightforward. It's a little goofy. Sometimes with weird geometries, you can find other lookup tables. And if it's really funky, sometimes the SolidWorks buckling analysis is your best friend sometimes. It's a little weird. I'm not very familiar with it, but I do know it exists. And it's something that you can always look into. And yeah, y'all better pull up on Saturday. And y'all better be freaking ready. Alright, ciao.